let's examine when the momentum of a system is constant and apply that to solving problems. First, we'll revisit the impulse equation. On the left, we have the impulse, the integral of the total external force acting on a system between some initial and final times. And on the right, we have the change in the total momentum of the system between those initial and final times. In a situation where the impulse is zero, we have that the change in the momentum is zero. P initial is equal to P final. In other words, the momentum of the system is constant between some initial and final time. This is a vector equation, but in many problems, we can set up our coordinate system so we only have to consider one dimension. Here's a simple example of one block moving along a horizontal surface with some initial velocity, colliding with a block at rest, and then the two blocks stick together and move. Is momentum constant during this collision? To answer that question, we need to think about what our system is. Let's look at the system of both blocks together. We can see the external forces, gravity and the normal force, add up to zero. So our total external force is zero. During the collision, each block exerts a force on the other, but that is an internal force if both blocks are included in our system. You can see that if our system was just one of the two blocks, we would need to know the collision force in order to solve for the final speed. Therefore, we will choose our system to be the two blocks together. We then need to set up a coordinate system. We'll pick the origin here, and this direction to be positive x. Now we need to identify the initial and final states. Our initial state will be just before the blocks collide. The momentum of the system is the sum of the momentum of each block individually. We have m1 times v1 initial x times I hat plus m2 times v2 initial x times I hat. This second term is 0 since block 2 starts at rest. The final state is right after the collision when the two blocks are moving together. They have the same velocity, so the final momentum is m1 plus m2 times v final x times I hat. This gives us an equation that will allow us to solve for whatever quantity we are not given. Now let's look at a similar collision, one that's happening in two dimensions. If we have one block coming up from the bottom, hitting one that's coming in from the side, I'll choose my unit vectors to be like this, my origin here. The momentum equation gives us two equations, one along the x direction and the other along the y direction. Once again, I'll choose the initial state to be just before the collision and the final state to be just after the collision. The momentum in the initial state is again the sum of the momentum of each block individually, and the momentum in the final state is the mass of the two blocks added together times the velocity of the two blocks. Notice that this velocity has a component in both the x and the y directions. Again, the total external force on the system is 0, so the impulse is 0 in both the x and y directions, and therefore momentum is conserved for both the x and y components. So I can write my two momentum equations like this. The impulse equation is a vector equation, so generically in two dimensions we will have two equations. We always need to check that the momentum is conserved in each direction separately, and it is possible to have a case where momentum is conserved in one direction but not the other, if we have some net external force in one direction. What would happen if, in our 1D collision example, the blocks now experienced friction along the surface? Can we still assume that the momentum is conserved? In fact, if we pick a point in time right before the collision and compare that to a point in time right after the collision, we can see that the impulse from friction is over such a short period of time that the impulse is really, really small. And we can say that the momentum is approximately constant. If we consider times later after the collision is over, then momentum is certainly not conserved, which is what you would expect. You'll see the two blocks slow down due to friction. So even if there are other forces acting on the system, like friction or gravity, we can still calculate the result of a collision as if the momentum is constant during the collision by picking times only a very small delta t apart.
We would like to now introduce a new methodological tool for analyzing problems that involve momentum transfers, and we call that tool momentum diagrams. Now, what we'd like to do is look at our fundamental idea, which was for discrete objects. We have that involved in a collision. We have that the external force integrated with respect to time, impulse, is equal to the change in momentum between two different states. So this is the momentum of the final state, and this is the momentum of the initial state. So when we want to analyze problems, how can we methodologically introduce a picture representation of our problem? So let's look at what we need to do first. We always need to choose a system that we're referring to. And with respect to the choice of that system, we need to also choose a reference frame. Now, once we've done that, we can now represent a collision with respect to this system. For instance, let's consider two objects as our system, object 1 and object 2. They're moving on a frictionless horizontal surface, and we're choosing as a reference frame the ground frame. Now, what we'd like to do is identify two states. So for our initial state, we'll have, if we're given some initial conditions, what we'd like to do is represent each object with a velocity vector. So here we'll write v1 initial, and let's suppose this object is coming at it with v2 initial as an example. And once we've represented the velocities of the objects, we can write down their momentum in the initial state. Similarly, if these two objects collide and they're moving, we actually don't know which way those objects will end up moving. And so what we'd again like to do in our final state after this collision is to represent the velocities by, again, vectors. So this is v1 final, and this is v2 final. And then we can represent the change in momentum. So our momentum principle now becomes, in this case, let's just assume that the external force here sums to 0. We're assuming no friction. And then our momentum principle says that 0 equals p final minus p initial. And now we can read off those momentums as vectors on the diagram. And so what we have is that the final momentum will be equal to the initial momentum. So we can write down m1 final plus m2 v2 final is equal to m1 v1 initial plus m2 v2 initial. And that's how we can represent a collision where there's no external forces and use our momentum principle to get a vector equation. Now, in many problems, you're given information. You might be given information about the speeds and magnitudes of the objects. And in order to then take this equation and represent it in speeds and directions or even components, we need to choose some coordinate system. So if we choose a coordinate system, and that's the third step, so suppose we choose a coordinate system, then we can start to look at two different representations for our problem. For instance, let's just choose this to be the I hat direction. Now, given that choice, we could describe the velocities in terms of components. Now, this gets awkward. v1 I x component I hat. And similarly, we can write down all the velocities v2I as v2 I x I hat etc., for all the velocities. And our momentum equation in components then becomes, in the I hat direction, m1 v1 ix plus, well, here we have the final state, so let's make this consistent, the final, plus m2 v2 final x equals m1 v1 initial x plus m2 v2 initial x. And that's the same equation that we have as vectors, now expressed in terms of components. And recall that components can be positive or negative.